Thank you, and thanks for inviting me here. It's always nice to be back in Bonn. I've prepared let's say lectures, but there's also a possibility of doing exercises. And so I would like to ask you, the audience, to choose between two options. Option number one is I spend 4 times 75 minutes talking. Option number two is I spend maybe 20 minutes less talking per lecture, and then together we spend 20 minutes trying and doing and succeeding or not succeeding and talking about it exercises. And so I would like to see, are the options clear? I would like to see hands for those who would like to hear 75 minutes of me. You can see that I can't really imagine anyone wanting this. or to have 20 minutes of exercises. Yeah? Okay, so option number one is 75 minutes of lectures, no exercises. Again? You can do that now. Anyone who wants 75 minutes of lectures without exercises, raise their hand now, or forever hold your peace. Anyone who wants 20 minutes of exercises and 75 minus 20 minutes of lecture, raise their hand. Okay, that's the majority. Okay. This would also be my preference, as you probably noticed by now. But okay. What I'm going to talk to you about, what I want to tell you about, is stuff that arose for me personally because there were things that puzzled me, and I wanted to understand what was going on. And so the main puzzle for me at the time was the following. In 1998, I read the paper by Felix Otto and Kindler and Jordan about the Wasserstein gradient flow structure of the Fokker-Planck equation. And this answered a couple of questions that I had at the time and raised more questions that I didn't have yet at the time. And but really what was kind of bothering me in the years after that was the fact that in the years after the development of the JKO scheme, as it's known now, and the whole world of Wasserstein gradient flows, it became clear that there are a large number of well-known differential equations, well-known PDEs, evolution equations, which all either are themselves Wasserstein gradient flows or are somehow part of a larger structure in which there's a Wasserstein dissipation. And so this meant that there suddenly was a large class of evolution systems which had been studied extensively in the mathematical community for 50 or 100 or 150 years sometimes. Well-known equations that we all knew, we thought we understood what they were like, we understood their properties, we understood their structure, we thought. And then suddenly in 1998, someone comes along and said, but there's much more structure that you didn't know about, did you? And so it turns out that this structure is not only relevant just because it's a nice, interesting structure, but it turns out to be thermodynamically relevant in a way that I hope to explain to you too, and where that's kind of, for me, became clear in the years after this. But there were bits there that were still very surprising to me, and the most important surprising bit to me was the question of the Wasserstein metric itself. The question, if we have all these physically relevant equations, well-known physical, we'll put them on the board in a moment, well-known physical equations have been studied for hundreds of years, and then suddenly comes along this gradient flow structure which has a Wasserstein metric in it, which has let's say at the time, at least for me, it had a derivation, a description, a definition, which had nothing to do with physics. So you have all these physically relevant equations, and you have an object in there that didn't seem to have anything to do with physics. And so I wanted to understand why. And so what I wanted to do in these lectures is I want to show to you a little bit why this is the case. So in answer to the question, why are there so many Wasserstein gradient flows? How can we understand that from a physical and then eventually mathematical point of view? And this ties in with another, let's say, thing that I've been doing for most of my working life. I've always been interested in modeling. And so one of the things that I discovered while thinking about these things is that the gradient flow structure itself is an extremely useful tool when you're modeling real-world systems. And I think I gave these lectures the title variational modeling and then some other stuff. And so variational modeling for me is a process of modeling where you model a system by writing down what you think is the driving energy and what you think is the dissipation mechanism that's stopping from going too fast. And once you've done that, out comes the equations, the differential equations that you might want to solve numerically, for instance. But if you're doing that, if this is the way you're working, and you have a skeptical person sitting on the first row who's going to ask nasty questions about why exactly do you write down this free energy, and why do you think that you... Right? The first row is always the worst, isn't it? And then the... No. So then, I mean, you have to have your answers, right? You have to have your answers ready about why this is the right thing to do, why this is the right free energy, why is this the right dissipation mechanism. And let's say a couple of years ago, I was in the situation that I intuitively knew Wasserstein is the thing to do, but I had no explanation other than it just feels right, which is not very convincing for the first row of the audience. So I also want to do that. I want to kind of explain to you a little bit where these things come from, why they pop up in so many systems, and that'll also explain how to model systems using those. I won't spend much time on that, but it will be somehow in the background of what we're talking about. Okay, so let's get to some examples, shall we? Lecture 1 will be basically about gradient flows and their generalizations. And so for the moment, my most important example will be those of Wasserstein gradient flows. And so now this is a good moment to ask, who knows what I mean when I say a Wasserstein gradient flow? Let me see hands. Excellent. Could you give me an example? Could anyone else give me an example? Sorry? Heat flow. So I'm going to work in continuous space. For the discrete stuff, you have to talk to Jan. But can you give me an example in continuous space of a heat flow? Say again? Yeah, so the equation would be something like this. Let's use rho as the variable for let's say, the unknown. And you say this is the Wasserstein gradient flow, which I always abbreviate as WGF, of entropy. Yeah? We'll write down a version of the entropy in a moment. Let's have another one. Another equation, which is the Wasserstein gradient flow. Sorry? Fokker-Planck. I can probably add this in here, I guess, right? Plus the divergence of rho times gradient into some potential. And this is, how do I change this? Plus some potential energy, okay. Another one. Interaction potential, very good. What do I do here? I want to use words for the moment. Interaction energy. Good enough. Another one. Force medium equation. Do you have a preferred way of writing that? Do you have a preferred way? No? Which is Wasserstein gradient flow of what? Sorry? I guess now we have to be more precise. Which entropy exactly? Say again? Rho to the power n plus 1. And I guess you probably need a constant here, which is of the form. I have to think about that. Okay. Some constant. Yes, very good. Any more? With another? Yeah, I'll come to that in a moment. If we decide to change this part, and we want the same equation, we can often get that by also changing this part. At the moment, I want to focus just on Wasserstein gradient. I'll get back to the other one. Another example? Higher order equations, anyone? Huh? Well, one of them, of course, is going to look like this. I need a minus sign then. This is one special version of what is of a sequence of a continuum of problems known as the DLSS equations, or it's also a thin film equation. So this would be a Wasserstein gradient flow of the Dirichlet integral. I mean, there are many more. Sorry? Say it again. Is it the square root of rho? No. No, I think this is right. No? Sorry? I think it is. We'll come to it later. Okay. We'll do some more examples later. But what I want to do at the moment is I want to move towards what I call generalized gradient flows, because I still consider these to be gradient flows. But I want to generalize in the following way. So I was going to move the other way, but maybe the best thing to do for me is actually to, do I want to do that? Yeah, maybe the best way to do is do differently than I had planned and simply write down a definition. Right? And this will be an example. So I define a generalized gradient system to be a triple, a state space, an abstract state space set for the moment, a functional, and an object that I'm going to call psi. And so for the moment, working completely formally, we're just going to think of Z as any set, but in practice it will have to have some kind of differentiability conditions. But for the moment, just let me call it a space. We'll see about the differentiability conditions in a moment. F is going to be the object that drives the evolution, which in this case would be these kind of combinations of entropy and other things. So F is going to be a functional that drives the evolution, and psi is going to be something that lives on the tangent space and that has a couple of nice properties. So the fact that it lives on the tangent space means that psi depends on where you are, and it takes a tangent vector. Let me call that V. And so what are the nice properties? Well, the nice properties are that for every Z, what are we doing here? The mapping, so for fixed Z, the mapping that takes V to psi of V is non-negative, convex, and 0 at 0. So when I say it lives on the tangent space, to whom does that make sense? Yes. So to start, I mean, much of what I'm saying here is formal, and there's a reason for that. It's not that I mean, most of my work is actually rigorous, but in this case, I prefer to be formal, and the reason is maybe twofold. The first is sometimes life is easier when you're formal. That can be useful. But the second is that when you're trying to understand why things are true, then sometimes the details get in the way. And so it can be useful if you really want to understand why, to skip the details to start with. And then afterwards, if you really want to know the rigorous details, you can kind of fill them in. But to start with, the best thing to do is to skip the details and just work formally. So basically, the 4 lectures that I'm giving here will be completely formal. I mean, as we already know from the work on the Wasserstein gradient flows, in these settings, it's often useful to think in terms of manifolds. These would be examples of that, and so we need to think in terms of that. At some state z, you're going to have some kind of local structure which will be given by psi. Okay, and so in addition to psi, I need its Legendere transform. So let me define that thing. So Gero already wrote this down. Legendere transforms are my friend in this work. They really are. They make life easier. Yeah. Yeah. Bring them on. I mean, just to be precise about what exactly I mean by Legendere transform, in this context, the relationship between psi and psi star is completely local. You fix z once and for all, and only think about the dependence on the 2 other variables. So you take a supremum, if you're calculating or defining the psi star, you take a supremum over all v in the tangent space at whatever z you're looking at, of a duality bracket between, this is a psi, psi is clear, between psi and v minus psi of v and z. And so if you want to put spaces here, then v lives in the tangent space at little z of the space big Z, and psi lives in the cotangent space, so that's the dual of that object. And this is a duality bracket. So to whom does the statement duality bracket make good sense? Let's see fingers, please. Sorry? The word, huh? Does it make sense? Yes. Does it make sense? Yeah? Okay. There's something going to be slightly confusing, which is that in practice, very often, we never like this abstract object. So we immediately replace this thing by something that behaves much more intuitively, which would be the L2 inner product on some kind of underlying space. And there's nothing wrong with that, because we're working formally anyway. And so this boils down to saying, well, we're just looking at some subset where you can parameterize the dual by bits in L2 in some nice way. In practice, it never gives you a problem when you're working formally. But sometimes it's confusing, because then at this level, you're thinking of an abstract dual object, whilst here suddenly the thing has become a function. So I'll try to make it kind of clear to prevent confusing here. I'm not quite sure I'll always succeed, though. This is just part of the folklore of this field. Okay. I was defining a generalized gradient system. It consists of three parts: a space, a function that's supposed to drive the evolution, and something that I call a dissipation potential, which I haven't written down yet. Okay. So for those who know what a gradient flow is, why do I need a dissipation something? Why do I need to define anything that I call dissipation? Yeah, that's a very good way of saying it. Suppose that I would like to write down, so what would a gradient flow be in this context? Well, that would be a time derivative of z should be equal to minus some kind of derivative of f. So let's take, I will always use d for the abstract Fréchet derivative of f. This doesn't make sense. Why not? Because this thing is a tangent object, and this thing should be a cotangent object. So I'm not even allowed to write down equality here. So to start with, I I'm not even allowed to write this. We'll see later that there's an additional reason why we need a dissipation structure, because it's part of the modeling. Actually choosing which missing information is going to go in here is actually an important modeling step. We'll see that later. So this is not going to work. That's why I need my psi. And so given such a triple, the induced equation, also called the generalized gradient flow, I mean the system is the triple and the flow is the equation, would be the following. You take z dot and you require it to be equal to the derivative of psi star calculated at minus the derivative of f at z at the point z. So you can see in comparison to here, what I've done is I've mapped this right-hand side through the behavior of this d psi star object. And just to check that at least the spaces now work out correctly, so let's do that little calculation. So psi lives on tz. This on tz, which means that the derivative of that thing is a linear, hopefully continuous mapping from tz to r, which means that d psi is an element of tz star. And if I repeat the same the other way around, I found that d psi star is always an element of tzz. So it maps. So it maps something that's an element of the dual to something that. Yes. Yeah. So that's the reason why. Yeah. So my use of the semicolon is supposed to indicate this. Right. The fact that here there's a. So let me. The meaning of that means that when I decide to differentiate this, I never, ever differentiate with respect to position. I only ever differentiate with respect to the variable that lives on my tangent plane, or in the case of psi star, of my cotangent plane. Does that answer your question? Say that again. D of psi dv of dot. Yeah. But I mean, you can also just remember, from all the points of view, you never differentiate with respect to z.
Once you've written,
okay, good. Anyway, so this ends the definition. It says, okay, given such a triple z f psi, then okay, by definition, the evolution equation generated by that triple is this evolution equation. So now let's check that this coincides nicely with a couple of things that we did over here. Right? Anton looks like he doesn't believe it. So let's take example number 1. So, yeah, go ahead. Yeah, sorry. Yeah, so let me, I think I'm being sloppy here. Let me be more precise. Let me, okay. I think you're right there. So let's forget about the little z, right? Because everything is fixed little z anyway. Yeah? So that means that we're looking at a psi which maps tz to r. Another way of that is saying that psi of v, we call it, is in r for every v in tz, right? Now that means that d psi of v at a point v, d psi is an object that I can contract against something that I might call v tilde, an alternative an alternative element of the tangent space, and then I get something that again lies in R, which means that the psi at V is an element of the dual space of the tangent space, right? So that means that the psi as an object applied to whatever in here is actually a mapping from this object, which is a tangent, to the whole thing, which is a cotangent. And that's what I need here. Go back here. Because I need to take an object. I mean, this is now the other way around, of course, because you have psi star. So I need to take an element that's in the cotangent. I need to map it to something that's in the tangent equation. I have a feeling that this only makes things more confusing. No? At least to one person, not. That's good. Sorry? Yeah? Okay. Okay, so let's take an example. Let's do the entropy plus the potential energy. So now we take for Z, we take P2 of RD. Probability measures on RD if you wish, if you don't care about the two. And so we take as the functional, we take, let's say, that combination of entropy and potential energy. So that would be f of rho is the integral of rho log rho plus rho times v. If rho is Lebesgue absolutely continuous and otherwise plus infinity. So, whilst we're at it, we might as well say that means that the derivative of f in the direction of some rho tilde is equal to the integral of log rho plus 1 plus v times rho tilde. Yeah? Yes? Yeah? But, okay, good. But in practice what people use, of course, is not this one. They use the variational derivative, which I'm going to write as curly delta, which is going to be the thing here on the inside. That's exactly what I meant by the red part. If you replace the abstract bracket by the red L2 inner product, then you find a different object. You find something that looks like this. And so it'll be useful to think in terms of the red things, which I'm going to write in terms of these deltas instead of the straight D's, which is somehow an abstract notation. It gets cumbersome. Okay, so now what is, so now we think of psi, and in this case it's easier to define psi star, which depends on position rho. And so if we're doing the Wasserstein dissipation, then it means that this is, yeah. And so maybe I should write this in red because, again, I'm using this notation, this representation of the dual in terms of L2 inner products. So that means that I'm applying it to a function, and I can take the derivative of a function, I hope, and calculate this norm, and then get a number out of it. And so if I take the variational derivative of this object, this is like differentiating that thing with respect to psi, and I hope that many of you will at least follow me if I say that this is the same as the divergence of rho times the gradient of psi. Yeah? At the end of the day, the choice between straight D's and curly D's is just a question of how you decide to parameterize your cotangent bundle. It doesn't change the content, it just changes your notation. Okay, so now the claim is that this thing here, this Z, this F, and this psi star together should generate, let's say, the first two lines of that equation, right? So let's try that. So that we should get the equation rho dot equals curly D applied star applied to minus the curly D of F at rho. Yeah? No? How do you mean? In this case, I simply define it. Yeah. Oh, so now I understand. Yes. Of course, in Legendere transforms, if everything is convex, then one completely defines the other. One of the many reasons I like Legendere transforms. Okay, so let's calculate this thing. This says it's equal to minus the divergence of rho times the gradient of whatever went into the psi part. And so minus df was equal to this thing. So get rid of the plus sign. We get the log of rho plus 1 plus v. And indeed, if we work this out, we find this is the same as Laplacian of rho plus the divergence of rho times the gradient of v. I'm not quite sure how to make sure that everybody can see everything. Yeah. Which one? Oh, this. Sorry, this is my semicolon. It's the same. It should be the same one as this one. Yeah. Sorry. That's probably a safe assumption, yes. Yeah. Okay, so now which one of you was familiar with the let's say the Wasserstein gradient flow structure that we just wrote down? Not in this form, but in a different form of this combination of Wasserstein metric on one hand and free energy or entropy plus potential energy on the other hand. Let's see hands. Who is familiar with this structure to start with? Not many? A few? So for the moment, this looks, I guess, at least to me, it looks like a very complicated way of either deriving or writing down a fairly simple equation, which is time derivative of rho equals Laplacian of rho plus divergence of rho times grad v. Sorry? Huh? It's just the Fokker-Planck equation, exactly. Yeah. And so the reason for having these generalized gradient systems, for thinking of them as slightly more, let's say, structures that live at a slightly higher level of abstraction, we'll come to, especially in the fourth lecture, where I want to show you that the things that we did in the second and the third lecture actually are extremely general. So general that they apply to a very wide class of systems. And then it turns out that for that generality, these generalized gradient flows are exactly the objects that you need. But for the moment today, I just want to talk a little bit more about these generalized gradient flows, and hope to make you slightly more familiar with their properties. So, gezondheid. So to start with, I need to say a few things about Legendere transforms in general. No, that's a good point. I can say that right away. In this example, psi star is a quadratic function of psi, and by Legendere transform properties, psi is also a quadratic function of its argument. And there are many examples of that type, and to be precise, the things that are usually known as gradient flows all have this property. They all have the property that their dissipation depends quadratically on whatever goes into it. And that's obviously an important class. And for instance, the discrete space gradient flow structure that Jan Maas, I think, wrote down early this morning. I wasn't there, but he told me about it over lunch. I'm guessing that that was similarly of a type where psi depends quadratically on its argument. Is that right? There are important other examples. One of them is the example of chemical reactions, which have, in a way we'll see later, a natural representation as non-quadratic gradient flows. One of the exercises in the exercise set today is about that. Another well-known example is of rate-independent systems. Rate-independent systems are systems which have a psi which depends, so the psi depends in one homogeneously, not two homogeneously, but one homogeneously on its argument, and correspondingly the psi star is an indicator function of some set. Okay, so just a few properties about Legendre transforms. So suppose I have phi, and let me say phi on a space Z, and phi star on Z star. These are a Legendre pair. Yeah? Say again? Important. Yes. I think you wrote a paper about an example where it's not that like that. Right? In which case, you will agree with me, it's not a gradient flow either, right? There's no way you could call that a gradient flow.
I mean, for example, this one
Say it again. This psi star? Yeah. It satisfies a stronger property then? Yeah, so there's one important thing. I mean, if you have a Legendre pair, so that what does that mean? That means that phi star of, so let's just forget about the z and just do it kind of locally. Phi star of z is equal to the supremum of psi z, let's call it v, minus phi of v, supremum of v, and phi of v. The fact that this is a Legendre pair means you can go both ways. Now you can, just by looking at this, you can see that if you have a Legendre pair, you can always add a constant to phi, which will make it subtract from psi star, which will make it subtract from psi star, which will make it add it to phi. So it's perfectly acceptable to add a constant to phi and subtract the same constant from psi star, and then you have another Legendre pair. And in practice, this doesn't change anything about the properties. So you're right that somehow the fact that they are non-negative, that psi is non-negative, minimized at 0, that you have to take up to a constant. Yeah. So important properties of this are especially the fact that, so the first one is the fact that there is an inequality for v and psi. And the second one is a characterization of when that inequality is actually saturated. So, for instance, you can ask the question, for which v, given v, for which psi can I make this inequality into an equality? And so there's a characterization which says the following. It says that you have equality. You have cases of equality if and only if v is an element of the subdifferential of psi star at psi, or equivalently, psi is in the subdifferential of phi v. If you don't know what the subdifferential is, think of a derivative. In our cases, we'll be thinking of differentiable functions, so subdifferential will just be derivatives. But so it tells the important fact, namely that I can characterize when you have equality in terms of kind of relationships between V and derivatives of the psi or the psi star. And so, for instance, that induced equation, if you look at that for a moment, then you see it's actually of the form of this one, right? So let's say that, in fact, that induced equation, z dot, and let's just do the case where everything is differentiable, so then we have no subdifferentials, we have normal differentials. So the fact that z dot is equal to d psi star of something, according to this characterization, is equivalent to that something being the d psi of z dot. Right? And it's equivalent to equality in this inequality. It's equivalent to the fact that z dot minus d psi of z is equal to psi of z dot. That's psi star of minus df. Right? It's just a direct translation of property B here to the thing we have over there. And so this will give us an extremely important alternative characterization. That's the following, that says, so this is now a lemma. So let's call this equation star any of the three forms of it. There's a kind of a trivial result that says that, so let's say any curve z in z solves star, which could be any of these three, or that one over there, if and only if we have the following property. We have the property that that if I look at the value of f at time t minus the value at f at time 0, plus the integral 0 to t of psi of z dot at time t, z at time t, plus psi star of minus d f z z also at time t dt. So if I look at this long expression, then this is, in other words, so this curve is a solution of that equation if and only if this long expression is non-positive. And this has a very simple proof. If I take any curve z, I calculate the time derivative of f of z along this curve. I find that it's, by the chain rule, that's equal to that. And I like things with a minus in front of it, so I'll put a minus there and there. And so for any psi in V, I have this inequality. So for any psi in V, I can estimate this by minus psi of z dot minus psi star of minus df. That's just this property over here. For that, I don't know. I mean, I can do this for any curve z because it holds for all psi in V. But then when I integrate this thing from time t to time, from time 0 to time t, I find that this thing over here, this box, which is exactly what I get when I take the right-hand side to the left and I integrate over time. I find from this inequality that this box is non-negative. So this tells me that for any curve z, this box is non-negative. If it's also non-positive, it has to be 0. And then going back, if it has to be 0, that can only be the case if this inequality happens to be saturated for every single t, or at least almost every t. And if this inequality is saturated for almost every t, that means by this characterization, or by this one if you want here, that this equation over here had to be solved for almost every t. So if the block is also non-negative, then the block is 0, and that means that indeed z dot is equal to d psi of minus df z for almost every time. Exactly, yes. Yes. So to give due reference to where this came from, I learned it from, like so many things, from Stefan Luckhaus, who was kind of involved with this early on but never wrote anything about it as far as I know. And it's related to the work in the De Giorgi group, where De Giorgi had the same property, that he did lots and lots of stuff, but hardly ever wrote anything about it. Other people, luckily, sometimes did, so that was good. But indeed, that's, both of these people were kind of early on proponents of thinking about more general gradient flow structures in this way. Yeah. Yeah. Sorry? Psi star, yes, thank you. Yeah. So to go back to this proof, so what it tells you is that if you take any curve, then you always have one inequality. If you require the other inequality, you have 0. 0 at almost 0 at all times tells you that you solve the equation at all times. And vice versa, if you assume that you solve the equation at all times, then you have the block equals 0, and that satisfies this inequality. So this proves the lemma. And so it turns out, at least, in a surprising way, at least to me, that if you think of this thing here as a placeholder for a simple equation like the Fokker-Planck equation, it turns out that in many ways, this thing inside the box, or this condition, including the inequality, that this box inequality is actually an extremely useful thing to have. It turns out to be much more useful than many other formulations, like the 3 you have up there, or any other one. This is from both a mathematically and a physically, from the mathematical and a physical point of view, this is an extremely interesting formulation, despite the fact that it looks large, ugly, and unwieldy. And but still, this is somehow the right way to think about it. What's the time? Okay. Anyway, so just to recapitulate what we've done until now, we've defined the concept of a generalized gradient flow. We've said, so that means that there's somehow this equation over here. We checked in the case of the example that that this is the that if you choose things the right way, then you get the equation that you hoped to get. So one thing I want to do before we start the exercises is I want to talk about why it is actually reasonable to say that this definition here can be called a Wasserstein gradient flow. Because I used the Wasserstein word, but I don't know if there's anyone in the room to whom this is obviously generating a Wasserstein distance. Is there anyone? Hands for anyone who says, I understand why this thing produces the Wasserstein distance. 2 maybe? Okay. Checked once a long time ago. Yeah, okay. So let me, before we do the exercises, let me just show that. Okay. So there are different ways of thinking about the Wasserstein distance. And in this context, the most useful one is one that I'm guessing that Jan Maas already mentioned, the Benamou-Brenier formula. You must have mentioned that, haven't you? Well, you're welcome to hide in the bathroom if you don't want to hear the answer. You want to do it yourself, don't you? No, I think it is good if you do this centrally. So the point is really this. So we've defined a psi star to be this object. Let's say we're working on some domain omega, and so I claim that if I now use the definition of Legendere transform, I work out what the corresponding psi is. I claim that this is equal to the integral of rho times the grade of p squared, where we find p based on v and rho by solving the equation p plus divergence of rho times grad p equals 0 with Neumann-boundary conditions on the boundary. So you think of this formula as working as follows. You know what v is. You solve this elliptic equation in p for given rho and v. That gives you your p. You stick in the p there, and you get the number. So I think André would probably prefer to write this slightly differently. I'm guessing that he would prefer to say, well, if you think of psi star of psi of rho as being 1/2 times psi plus 1 comma rho, so this is somehow a plus 1 Sobolev semi-norm with weight rho, then somehow it's natural to think of the dual as 1/2 v minus 1 rho, the corresponding duality norm. Does that make sense? No? Whatever you choose, the bottom line is that now, if you define the following object, the distance between a rho 0 and a rho 1, by the infimum of the integral over a time 1 interval, the integral over space, well, let me do it like this first, of psi of rho t dot time derivative rho t dt. If you define this object, then this turns out to be exactly the Wasserstein metric. Because over here is exactly the Benamou-Brenier formula. Because of this thing here, you think of this is a flow field, call it W. And this is 1/2 rho W squared under the condition that V plus divergence of rho times W equals 0. That's exactly the Benamou-Brenier formula. So the right way to interpret this is to think of, if you have this pair of a psi and a psi star, then what the psi is doing is it's telling you, in some sense, how much energy you're burning when you're moving with a velocity v. The same way that the Benamou-Brenier version of the distance tells you how much instantaneous energy you're burning when moving at a velocity given by the argument in there. And then psi star somehow appears naturally in the variational structure of a gradient flow. Yeah, partly by magic, if you want. It's the magic of variational calculus. Yes, so I guess this is probably a good place to stop talking. And I have some exercises. why don't you hand them around? I'm not quite sure I have enough for everyone, but let's see. I think I have about 20 or so. Maybe nearly enough for everyone. Why don't you hand them to the back and see how far you get? And so I included some exercises about Legendre transforms for those who have not seen those before. It's useful to play around with them and to see a little bit how it works. And I've included some exercises about generalized gradient flows. And specifically, there's one example about how you can write the system of mass action chemical reactions as a slightly surprising generalized gradient flow, which will pop up in a way that we'll see later on in these lectures. So what I suggest we do is have a look at them yourself. I'll be walking around to answer any questions that you might have. He didn't ask a single question. What?
I didn't ask any questions. Write out completely the Benamou-Brenier, right? So it's just the end conditions you want.
Should I write that completely?
Just the end conditions, right?
So this is on the occasion. And then this thing here, you write this saying this is equal to the integral over omega of rho times rho t w t squared under the condition that the dt of rho t plus divergence of rho w. Right? And you take the infimum over all curves rho and w if you want. This thing really kind of minimizes over the w part. But if you want to do the full Brenier, you also need to minimize over the W. I'm sorry. Yes, good. Thanks. So there's a typo in the question 2b. I think it should be the sum of alpha I xi reacts with the sum of beta I, not alpha I. And then also, of course, yeah, good point there. So there's summation over I. And there are additional indices j, one for each reaction. How you doing? Yeah, the same thing went on there. Yes. Let's see. If you're moving from left to right, then I guess that's. Then you have to be. I mean, if there's more of this stuff than of that stuff, then you have to be moving from left to right, which means that the alpha component has to decrease, which means that has to be alpha. Can I borrow that for a moment? Reproduce. There's also a typo in the line below I now see. So the line below should read Ci dot equals sum over j of kj alpha I j minus beta I j times the product of I of k of ck over ck bar. I need a product. I need a product, yes. Remember, this is J. Yeah. Yeah. Did I miss parentheses? Parentheses. It's very iterative processes. Yeah, no, absolutely, yeah. Als je als C-concentratie gebruikt, even denken hoor. Nou ja, wat er dan gebeurt is dat je dan verschillende coëfficiënten voor die twee termen krijgt. Het is een verschil van twee termen. En die C-bar dingen die hebben niet noodzakelijkerwijs dezelfde. Of hebben ze het misschien wel? Kun je ze nog gewoon weglaten? Want als je de C-streep. Ja, misschien begrijp ik het. Als je C-streep stationair is, dan heeft hij de eigenschap dat. Ja, nee, dit is de manier, dit is de reden waarom je die coëfficiënt kj eruit kunt halen, zodat je maar één coëfficiënt krijgt. Yeah.
Okay, so take any of example. Given f, given equation,
Mm-hmm.
then size are not uniquely determined, right?
Exactly. Yes.
How could we pick up this?
This is large deviation rate function. It's a large deviation rate function.
Because any size sets up as a gradient.
Yeah. 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 I mean, of course, if you want, you can take, because you know, given z, you know what the value should be, right? So you can just make it independent of that if you want. Yeah. Yeah. No, so it's true. It's not uniquely defined. I wanted to give examples of that, but I didn't have time.
Resources that
Yes.
appear somewhere.
Yeah.
Recognize this in
Yeah. Yeah. It has a very simple phi star.
Can I have it?
No. Yeah. Ah, okay. Okay. Good. Yeah. Yeah. Okay. Very nice. Okay. Yeah. Yeah. In some cases, yes. You can kind of see what it's going to be in the general cases. I'm not quite sure that there's. Let me think. Is there? Is there a full LDP for? Yeah, there is. I have to think, but there's actually a proof somewhere. Too general? Yeah. Yeah, maybe I should have done that. Yeah. Or Alan Kahn or something like that. Or Alan Kahn or something like that. Or yeah. I was hoping on doing those examples here in front, but that didn't. So you write these things down? Just like, you write them like that, do you?
Sorry?
You write them just like that? Okay. You write them just like that? So your notes just like this? You write your notes directly on the screen?
No, it's just notes.
Yeah.
Otherwise, I don't find it. No search algorithms and stuff. Search Peletier.
Outcomes is
Not more than 100 things we come up with.
Yeah. Een beetje achter.
Niet gedeeld door de viscositeitsconstanties.
Nee, precies.
Maar
Maar
misschien
dan,
heb je andere-
maar dan heb je twee verschillende constanten.
Oké, je hebt al.
Kijk, het punt is, als je het zo schrijft, dan heb je voor elke keuze van C streep of van KJ, is het altijd reversible altijd bepaald. Het is een evenwichtsconcentratie in de praktijk. Ja. Dit is maar 1K. Je hebt een K plus en een K min.
Ja, precies.
En daar is het nummer 1, zie je? Ja, dus je kunt van de ene naar de andere rekenen. Hè? Dus je kunt inderdaad die KJ gedeeld door sommige product van de CK-strepen tot de macht BJK. Die kun je in jouw K doen. Ja, precies.
Ja,
Ja.
oké,
Ja, maar mijn punt is, er zit dus hier, hoe moet je dat zeggen? De reden waarom ik dit verkies, is dat hier is detail balance hard-coded. Voor elke keuze die ik maak, van C' en K, is dit detail balance. Ik heb geen verdere condities meer nodig. En dat is met name, we staan met I.O. produceren we allerlei, we spelen met verschillende systemen. En dan is het heel handig om altijd te weten dat het ding detail balance is.
Ja,
Maakt niet uit welke getallen je produceert, je krijgt altijd een detail balance systeem.
geen aparte parameter.
Nee, je hoeft niks meer te checken. Dus je hebt een makkelijkere parametrisering van je systeem. Maar er zit wel één degeneratie in. Je kunt net zien dat als je C-strepen met iets vermenigvuldigt en de KJ's met iets anders vermenigvuldigt, dan is het een vorm van degeneratie. Je hebt eigenlijk één minder echte vrijheidsgraad dan je parameters hebt. Maar goed, je hebt wel gegarandeerde eigenschappen, dus dat is prettig. Sometimes you can be very convenient and just replace everything by coercive and smooth. Then lots of things become simpler. Right? So then the sum of a subdifferential is automatically a subdifferential of a sum. And since you have kind of ways of, how do you say, of approximating arbitrary pairs by pairs which are smooth and coercive. So that means that you can argue by density in some sense. So it makes life simpler. I think it's time to stop. It's been a long day. How long do you want to continue? 5:45? Which is now, I think? 5:45. Yeah, so let's stop now then. Well, anyone who wants to continue here can stay. Yeah, so I think it makes sense to conclude now and say. Okay, it's 5:45. I'm told there will be wine and other good stuff waiting for us at some point. So I suggest to leave it here, and anyone who wants to continue later on during or after dinner is welcome to come and talk to me. Thank you for listening.